If a star the size of our Sun were to enter the solar system, what would happen? The distances between stars are so unfathomably massive that the chances of a direct stellar collision are incredibly slim. Space is, after all, mostly empty. If our Sun were the size of a standard golf ball sitting in the middle of Times Square in New York City, the nearest star would be another golf ball sitting all the way in Chicago. Between those two golf balls is nothing but a freezing, empty vacuum. Because of this immense, mind-bending scale, it is easy to assume our solar system is perfectly isolated and an encounter with another star is slim. But a slim chance is not zero. The Milky Way is a churning, chaotic disk composed of hundreds of billions of stars, all orbiting the galactic center at different speeds, on different inclinations, and with different gravitational trajectories. Over the multi-billion-year history of our cosmic neighborhood, the math dictates that traffic is going to cross, and a few stars have come close, very close. In fact, the gravitational scars left behind in our outer solar system suggest that one ancient star appears to have come closer to Earth than the Voyager 1 probe is right now. Welcome to territory. This is your space. Billions of years ago, when the Earth was little more than a violent, cooling sphere of magma, a rogue star came barreling toward our Sun. To see the scars of this encounter today, you have to look out into the freezing dark. Far past the orbit of Neptune is a massive graveyard of icy debris called the Kuiper Belt, and beyond that sits an even sparser, more chaotic collection of ancient rocks known as the scattered disk. If the solar system formed in complete isolation, standard orbital mechanics dictate that all of these objects should orbit the Sun on a relatively flat plane. Think of it like a vinyl record spinning on a turntable. They should all travel in the exact same direction as Earth and the rest of the planets, perfectly conserving the angular momentum of the primordial dust cloud that birthed our entire system. But they don't. When astrophysicists analyze this outer region, they find icy worlds on entirely anomalous paths. Many of them have wildly eccentric, highly tilted orbits that aggressively punch through the flat plane of the solar system at steep angles. Some even travel backwards in what is known as retrograde motion. The most famous example of this orbital chaos is a dwarf planet called Sedna. Discovered in 2003 by a team at Caltech, Sedna's orbit is mathematically bizarre. Instead of a neat circle, it travels in a massive, stretched-out oval path, stretching so extremely that its furthest point hits a staggering 937 astronomical units from the Sun. It takes Sedna over 11,400 Earth years just to complete a single lap. What force could possibly drag a 600-mile-wide dwarf planet nearly 1,000 times further away from the Sun than the Earth is? It would take a massive amount of kinetic energy to stretch an orbit that far. Researchers at the Forschungszentrum Jülich in Germany recently set out to solve this discrepancy. They ran over 3,000 independent computer simulations, constantly adjusting the masses, speeds, and trajectories of hypothetical objects to see exactly what kind of gravitational disturbance could reproduce the specific chaos we observe today. They found a perfect mathematical match. Billions of years ago, a rogue star weighing roughly 0.8 solar masses slammed into the outer edges of our solar system. It buzzed past the Sun at a distance of just 110 AU. To put that scale into perspective, 110 AU is closer to Earth than the Voyager 1 space probe is right now. The gravitational shockwave from this encounter permanently tilted the orbits of millions of icy bodies, throwing them into the bizarre alignments we see today. But it also did something else. It knocked a massive amount of debris inward. As these dislodged, frozen rocks fell towards the inner solar system, the immense gravity of Jupiter, Saturn, and Neptune caught them. This perfectly explains why our gas giants have irregular moons, like Saturn's moon Phoebe, which orbits backwards and remarkably far away from the planet. The realization that a passing star could catastrophically disrupt our solar system actually stems from a wild, decades-old scientific manhunt for the Sun's evil twin. In the 1980s, paleontologists noticed a disturbing, undeniable pattern in the Earth's fossil record. Mass extinctions on our planet seem to happen in a cyclical rhythm, occurring roughly every 27 million years. To explain this morbid biological clock, a physicist named Richard Muller proposed an incredible, terrifying theory. The Sun is a binary star. He hypothesized that our Sun has an undiscovered companion star named Nemesis, likely a dim red dwarf or a faintly glowing brown dwarf, orbiting us at an extreme distance of about 1.5 light-years. According to Muller's math, every 27 million years, the highly eccentric orbit of Nemesis would drag it directly through the densest part of our outer solar system. Its massive gravitational field would dislodge billions of dormant comets, sending them raining down on the inner planets, and occasionally wiping out life on Earth. It was a brilliant theory. NASA took it so seriously that they actively scoured the sky using highly sensitive infrared space telescopes like IRAS and WISE, hunting for the faint heat signature of Nemesis hiding in the dark. But they found nothing. Nemesis does not exist. Our Sun is a single, solitary star. It forced astronomers to realize something far more profound. We don't have a permanent evil twin star orbiting us. We don't need one. The Milky Way galaxy provides enough rogue passing stars to do the exact same damage all on its own. Which brings us to an intruder that visited us while early hominids were already walking the Earth. Far beyond the Kuiper Belt and the scattered disk sits the Oort cloud, a massive spherical shell of icy debris that completely encases the solar system like a cosmic bubble. The physical scale of the Oort cloud is incredibly difficult for the human brain to comprehend. It stretches up to 100,000 AU into space, marking the absolute gravitational boundary where the Sun's influence fades into the interstellar medium. This distant, freezing region is the birthplace of long-period comets, the massive chunks of dirty ice that take thousands or even millions of years to complete a single orbit around our Sun. Under standard astrophysical models, the primary force that knocks these comets out of the Oort cloud and sends them plunging towards the Earth is something called the galactic tide. This is the general, ambient gravitational pull of the Milky Way's dense disk. Because the galactic tide is a uniform, predictable force, incoming comets should arrive from very specific, highly predictable directions based on the geometry of the galaxy. But when astronomers actually map the trajectories of incoming long-period comets, it does not align with the math. Instead of coming from one expected angle, they plunge into the inner solar system evenly from all directions, completely ignoring the galactic tide model. But a recent study published in the Planetary Science journal solved this mystery. By analyzing the trajectories of both new and returning comets, researchers identified a specific star that caused the anomaly, HD 7977. Roughly 2.5 million years ago, HD 7977 buzzed our solar system at a distance of just 6,000 to 10,000 AU. It ploughed straight through the Oort cloud. When a massive star passes that close to a reservoir of trillions of dormant comets, it massively disrupts their delicate gravitational balance. The repercussions of this event can be seen even today. Because the orbital period of these distant comets is so incredibly long, the gravitational disturbance caused by HD 7977 triggered a prolonged comet shower. We are currently living through the latter stages of it. This stellar flyby triggered a massive surge in the number of comets entering the inner solar system, resting roughly twice as high as the long-term historical baseline rate. We previously thought the Oort cloud was incredibly dense based on how many comets we see. The new research suggests that the Oort cloud is actually much smaller, and we are simply standing in the middle of a 2.5 million year old cosmic splash. Our next stellar visitor arrived much more recently. Discovered in 2013 and meticulously analysed by astronomers over the past decade, Scholz's star is a binary system. It consists of a small red dwarf paired with an even smaller brown dwarf. About 70,000 years ago, this binary system screamed through the outer edges of the Oort cloud. To put this timeline in perspective, Neanderthals and early Homo sapiens were actively hunting, building fires, and migrating across the planet while this star was passing through our solar system's outer territory. Scholz's star came within 52,000 AU, which translates to roughly 0.8 light-years. Considering that our current closest stellar neighbour, Proxima Centauri, is over 4 light-years away, a star passing at 0.8 light-years is a near miss of monumental proportions. It was practically in our cosmic backyard. Interestingly, despite its extreme proximity, Scholz's star was incredibly dim. Our ancestors likely could not see it with the naked eye. However, red dwarfs are notoriously volatile stars. They frequently unleash massive magnetic flares that can temporarily increase their brightness by orders of magnitude. It is highly probable that for a few hours or days at a time, Scholz's star flared violently enough to be seen from Earth, appearing as a faint, anomalous red smudge in the night sky to anyone looking up. But how do we actually know it was there? How do you track a star that left the scene of the crime 70,000 years ago? By analysing the star's current radial velocity, exactly how fast it is moving away from us, and its proper motion, how it moves across the sky relative to background stars, astronomers successfully ran the clock backwards to trace its exact historical path. The gravitational wake of this binary system permanently altered the trajectories of a specific subset of small bodies in the outer solar system, leaving a mathematically perfect fingerprint of its prehistoric greys. What do you guys think? Let me know by dropping in your comments below. And as always, don't forget to subscribe to Territory, because this is your space.